So we'll be solving question number 6 of the exercise 2.1 of the book Challenges and Thrills of Pre-College Mathematics. So in question number 6, we need to prove by induction that the product of r consecutive numbers starting from any number is divisible by r factorial. So so in order to prove the statement, we will be using induction, but we'll be doing induction on the R rather than the N, right? We'll be doing induction on R, right? So let's take the base case. So the base case is R equal to 1. So when we take R equal to 1, essentially what the base case statement is trying to prove is that all natural numbers N is divisible by 1, which is true because 1 divides every natural number n. 1 divides n for all n belonging to natural numbers, right? So the base case is true, right? Now for the inductive step, let's define some term into n plus 1 into n plus total n plus r minus 1. We will define n as the starting number, right? And in order to not write this entire sequence again and again, we'll define the sequence n into n plus 1 till n plus r minus 1, all of them being multiplied. And these are a total of r terms. We will define this as f of n, which is the starting number, comma, r, which is the length of the terms. So if we say something is f of n comma r, we mean that it's a multiplication of consecutive natural numbers which starts with n and has r natural numbers in total. Okay. So the inductive step, we have, suppose a is any arbitrary starting number or any natural number. Let's just say it's any arbitrary natural number, right, for which we want to prove that. So let's take the inductive hypothesis first. For the inductive hypothesis that the statement is true for all natural numbers r that are less than k plus 1, right? So since it's true for all natural numbers r less than k plus 1, we can substitute r equal to k. So we have that um, any product of k consecutive natural numbers is divisible by k is divisible by k factorial, divisible by k factorial. So these are inductive hypotheses, right? And now we're going to use that. So let's say we have um, a product of k plus 1 natural numbers starting from a plus 1. So we have a plus 1 into a plus 2 till a plus k plus 1, and these are the total of k plus 1 terms, right? And then we subtract um, a sequence of a similar sequence that starts with a, so a into a plus 1 till a plus k in, and these are k plus 1 terms, right? Now this proof might seem a bit unintuitive. So yeah. Now what we do is we take a plus 1 till a plus k common. So from the first term, when we take this common, we have a plus 1, a plus 2 till a plus k, right? And from the first term, we have a plus k plus 1. And from the second term, we have minus a, right? So this becomes a plus 1 into a plus 2 till a plus k into k plus 1, right? Now, if we have to write this in terms of f, this equation essentially comes out to be f of a plus 1 uh, k plus 1 minus f of a comma k plus 1 is equal to k plus 1 into f of a plus 1 comma k, right? Now we do the same procedure for, instead of taking a plus 1 here, we take a here, and here will be a minus 1. So we have f of a comma k plus 1 minus f of a minus 1 comma k plus 1 is equal to k plus 1 into f of a comma k, right? And then we keep doing this till we have f of 2 comma k plus 1 minus f of 1 comma k plus 1 is equal to k plus 1 into f of 2 comma k, right? Now, by the induction hypothesis, we have that f of anything, comma k is divisible by k factorial. So let's sum all of these. When we sum all of these equations, plus 2, right? When we sum all of these equations, the term, this term f of a comma k plus 1 gets is in subtraction, but in the next equation it's in addition, so essentially they get cancelled out. So this term and this term gets cancelled out, and similarly this term and the next term in this equation get cancelled out. So essentially in the end what we have is f of a plus 1 comma k plus 1 minus f of 1 comma k plus 1 is equal to k plus 1, we take it common from all of these right hand sides, and we have f of 2 comma k plus f of 3 comma k, and just keeps on going till f of a plus 1 comma k, right? Now we know that f of 1 comma k plus 1 is just k plus 1 factorial, and we also know that all of these terms, f of 2 comma k, f of 3 comma k, all of them are divisible by k factorial. So what we can do is we can write this as f of a plus 1 comma k plus 1 minus k plus 1 factorial is equal to k plus 1 into k factorial into m, where m is some natural number, right? So then we have f of a plus 1 comma k plus 1 is equal to k plus 1 factorial into m minus k plus 1 factorial, which is equal to m minus 1 into k plus 1 factorial, right? So we have that f of a plus 1 comma k plus 1 is equal to m minus 1 into k plus 1 factorial, which means that this term right here is divisible by k plus 1 factorial, which is essentially what we had to prove because this is a sequence of k plus 1. Um, this is a sequence of k plus 1 terms that are in product and start from a plus 1. So if we substitute a equal to 1, we get f of 2 comma k plus 1 is divisible by k plus 1 factorial and so on. And we already know that f of 1 comma k plus 1 is essentially k plus 1 factorial, which is already divisible by k plus 1 factorial. So that case is not needed. So if we substitute any natural number from 1 to infinity in the place of a, we get that all sequences that are consecutive sequences and have k plus 1 terms. When they're multiplied, they are divisible by k plus 1 factorial. And since the induction hypothesis was that these are divisible, the induction hypothesis was that this is true for all natural numbers R that are less than k plus 1. And since we have proved for k plus 1 by a principle of mathematical induction, we can say that the statement is true for all natural numbers R.